Hello friends, this is the first lecture of ray optics, and today our topic of discussion is relation between the focal length and the radius of curvature of a spherical mirror. Here we're going to prove this relation, and this was asked in Assam Higher Secondary Education and Council AHS final examination 2025, right? And if you need the PDF of this lecture, then please send a message to my Insta account. This is my Insta account, OJHALAKHYAJIT123. if you want to follow me on Insta, you can follow me, right? Send your WhatsApp number to this Insta account so that I can send you the PDF of handwritten notes, right? So before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. So now let's start. Suppose we have a spherical mirror. So let me take a concave mirror, right? This is suppose a concave mirror. Now you see, and this is the principal axis of this mirror, okay? And suppose this is an incident ray of light. Let me draw it properly. Incident ray of light, okay, which is parallel to the principal axis, right? So let me write it, just give me a second, okay, just wait. This is the incident ray, and let us consider this is the focus. Suppose here is the focus point, and here is the center of curvature. Let me take this is the center of curvature. Then you see this parallel ray, after reflection, it comes through, it reflected through this focus, right? Like this focus point, principal focus. And let me draw a normal at this point, and the normal at this point must be passing through the center of curvature. So just give me a second, let me use another ink here. So now you see this is the suppose normal at this point. So this is the angle of incidence, this is the angle of reflection. Both must be equal according to the law of reflection of light, right? So now let me draw a perpendicular from this point to the principal axis, okay? So this is a perpendicular, and this point of incidence is A. This is the point of incidence, and the foot point of the perpendicular is suppose N, and the pole of this mirror is suppose P here. This is the pole P, this is the pole, okay? And this incident ray is OA, and the reflected ray is AB through the focus, right? Now you see, if we take this angle is theta, right? Then this angle I must be also equal to theta, right? Because they are alternate interior angles, because these two are parallel, okay? This ray is parallel to the principal axis, right? These two are alternate interior angles, so I must be equal to theta, right? Hope you have understood this. And according to the laws of reflection, I is equal to R, so that's why this R must be also equal to theta. If that is the case, then again you see, as this is parallel to this one, so that's why this angle is alternate interior angle. These two angles here, you can see I have marked red, are alternate interior angles. So here you see this upper part is theta, lower part is also theta, this upper angle and lower angle. So this angle is 2 theta, this angle is 2 theta, so that's why this must be also 2 theta, right? So hope you have understood this. So this angle is 2 theta, right? So you have understood this one. So now let me write what I have considered here. So in the figure, the OA is incident ray at A, right? And let us assume that assuming OA is here you see OA is paraxial lay, paraxial ray. Okay, paraxial lay means this is very close to the principal axis. Okay, this here you see this is the mirror, and paraxial lay means this is very close to the principal axis, right? So hope you have understood this. On the concave mirror, right? Now here P is the pole. P is the pole of the mirror, is the pole of the mirror, and C is the center of curvature. C is the center of curvature, and F is the principal focus, right? And OA is parallel to CP. OA is parallel to CP. This incident ray is parallel to the CP, principal axis, right? Now reflected ray pass through, and the reflected ray passes through the focus F, right? And CA is the normal. CA, this one, this CA is the normal. Sorry, this is normal to the mirror, at the point A, right? And also I have drawn AN is perpendicular to CN, right? AN is perpendicular to CN, or you can say CP, right? This AN is perpendicular to CP, right? Now you see, by the law of reflection, I must be equal to R. That is by laws of reflection. Sorry, reflection, right? And here angle I and R, so both gonna be equal to theta. Okay, as I have considered this angle is theta, right? Okay, these two are alternate interior angles, this one and this one, right? And according to the law of reflection, these two angles are equal, so both must be theta. I R equal to theta, right? So first let me write one thing here. Okay, this is suppose equation number 1. This is suppose equation number 1. Okay, let me take this as equation number 1. Now you see let me copy this diagram and let me draw it on the next page as well. Okay, so as we're gonna use the diagram again, so that's why I have pasted the diagram here. So here you can see that AFN, this angle AFN, this angle is 2 theta. This angle is alternate interior angles. These two angles are OAF and AFN. These two are alternate interior angles, so these two must be equal. So we can say that, now let me use the black color. Angle AFN, angle AFN is equal to angle OAF. These two are alternate interior angles. Alternate interior angles, right? Alternate interior angles. So we can say that angle AFN is equal to, so now you see OAF from the diagram, this angle, you see OAF, this angle is equal to I plus angle R, right? Sum of these two angles will be equal to this angle, right? So we can say that we can replace this by I plus R, angle I plus angle R, and both equal to theta. So that's why we can say that theta plus theta, which is gonna be equal to AF, this implies AFN is equal to 2 theta, right? That's it, we can write. So hope you have understood this. So using equation number 1, because these two are theta, that was mentioned in equation number 1, right? So hope you have understood this. Now you see, from triangle ACN, let me take this triangle, you see ACN, this triangle, this is C, this is A, this is N, ACN, this angle is theta, right? Now you see, if you take the tan of theta from triangle ACN, tan theta is equal to AN by CN, right? AN by CN, AN by CN, okay, right? Now you see, from triangle AFN, this one, AFN, this angle is 2 theta from this triangle, and from triangle AFN, tan 2 theta, that's gonna be equal to AN by FN, AN by FN. Now you see, is the since the incident ray is paraxial line here in this case, that means this is the mirror, this is the principal axis, and the line, this incident ray OA is paraxial, that means this is very close to principal axis. Then this angle theta and 2 theta gonna be very small, okay, that's gonna be very small, right? So hope you have understood this. And for very small angle, that tan theta is approximately equal to theta. So similarly, tan 2 theta will be approximately equal to theta, right? Hope you have understood this. So that's why what we can write, since OA is paraxial ray, so theta is very small, hence tan theta is approximately equal to theta. Also tan 2 theta, that is approximately equal to 2 theta. So from this equation, if we use these two values, then what we're gonna get, right? So let me write that one. Then we're gonna get theta is equal to an by cn and 2 theta is equal to an by fn, right? So therefore we can write, therefore we get theta is equal to an by cn. Let it be, suppose, equation number 2, and 2 theta is equal to an by fn. Let it be, suppose, equation number 3. Let me rearrange this. So let me write this one here. So since theta is very small, we have got tan theta is approximately equal to theta. Similarly, tan 2 theta will be equal to approximately 2 theta. So from this above two equations, so the above equations becomes this two, right? This one and next one is this, right? So I have taken these two as 2 and 3, equation number 2 and 3. Now from 2 and 3, what we can write, you see, theta is equal to an by cn. So let me use 2 in 3. Okay, then what we gonna have? So if you use 2 in 3, then if you replace this theta by this value an by cn, then you're gonna get 2 an by cn is equal to an by fn, right? So what we have got, let me write this on the next slide. So this is what we have got. How we have got this? Using equation number 2 in equation number 3. So we have this is equal to theta, and we have put this theta here. Okay, so using 2 in 3, we have got that. Let me rewrite this here properly. 2 an is by cn is equal to an by fn. That's what we have got, right? Now let me clean it. Okay, now you see here an cancels. So an cancels. So what we have got 2fn is equal to cn. This is, suppose, equation number 4. Let it be equation number 4. Now what we can do next, if you see that since theta is very small, so let me draw the diagram here again. So this is the diagram. So now you see, for the paraxial incident ray, if this is very close to the principal axis, then you see this perpendicular, this point will be very close to P. Now you see, let me give you an example. This is the mirror and here is the principal axis. Now consider this ray parallel ray, this ray. Let me draw another ray. So now you see, suppose this is the center of curvature. If you have taken this, if you join these 2 points, then this theta will be larger. Okay, then if you consider this line, then theta will be smaller, right? Then if you consider this line, which is very close to the principal axis, then theta will be the smallest one in this case. Okay, compared to the first 2 cases, here it is very small. In this case, you can see, if you draw the perpendicular from here, then this point is far away from the principal pole. Okay, then if you draw the perpendicular from this point, this is very close to the pole. Similarly, if you draw the perpendicular from this point which is the incident point of this line, which is very close to the principal axis, then this n is very close to P. So we are actually considering this case. Okay, so though we have drawn this is far away from this principal axis, but to explain it clearly, to draw the diagram clearly, so I have drawn here, but we have to assume that this line is very close to the principal axis, like that. Okay, hope you have understood this. So in that case, n must be equal to n must be close to P. Okay, very close to P, right? Since OA is paraxial ray, so n is very close to P. That's why we can write that Cn is approximately equal to Cp, and also we can write that Fn is also approximately equal to Fp, right? So that's why this equation 4 implies, so instead of Fn we're going to write Fp, and instead of Cn we're going to write Cp. So equation 4 becomes 2 Fp is equal to Cp. That's what we have got, right? Now you see here, this Cp is nothing but radius of curvature, right? Cp is nothing but radius of curvature. So according to the sign convention, we're going to write minus r, and Fp, this Fp is nothing but focal length. So using the sign convention, we're going to write minus f. Okay, using sign convention. So this relation here, you see 2 Fp can be replaced by minus small f, which is focal length. This is nothing but focal length, right? And this small this capital R is nothing but radius of curvature, right? So let me write it properly. Radius of curvature. So Cp can be replaced by minus r. So here you see we can cancel minus both from both sides. So f will be equal to r by 2. This is what we wanted to show. So this is the relation that we want to prove, right? So hope you have understood this. So thank you for watching. See you in the next video. Bye bye.